all of this is well and good. We've dealt with one-dimensional motion here. We can get away with, we don't need I hat and J hat because we're just dealing with, we can get away with plus and minus. But what if it's a two-dimensional problem? Let's tackle the classic two-dimensional problem. Projectile motion. What do I mean by projectile motion? There we go. Projectile motion, right there. The classic simplest problem is I tell you what the initial velocity is and I tell you the initial position and you figure it out from there. That's simple, straightforward. I'll point out where I see the most mistakes. The key thing here is, well, we can demonstrate it. I have two markers here that I'm going to sling off the table. I should move this so that doesn't interfere with it. When I sling these off the table, the question is, this one will be going faster than this one. I'm going to flick it like that so that this one's not going to be pushed very far, this one will be pushed the farthest. It will accelerate more, or at a greater rate. This one will be going faster. And the question is, which one will hit the floor first?
One going faster.
So I've got to vote for fast. Oh, let's see if physics by democracy works. So we got the faster. So which one hits the ground first? Faster, slower, tie, neither. I will tell you right now, I'd like to do this bit again later, but neither is an homage to a comic I read growing up in which somebody bet that a hockey game that no one would win, and there was an explosion in the middle of the hockey game. Can you guess who the villain was? So anyway, that's what neither is. Neither in this case would be the person who claims all the way down and never make it. Let's just assume for the sake of this, it's just an homage, and neither is not the answer. All right, the faster one.
I think the faster distance to travel, or the faster when it fell to the ground.
It's coming off the table faster.
The green one?
The black one will be going faster.
So you're asking which one will reach the ground first?
Yes.
Okay, the green one.
Yeah, the green one.
All right, so for the black one, it'll be going faster off the table.
Yes.
Yeah.
No one says that. The slower one, the green one.
Yes.
So 1, 2, 3, 4, 5, 6, 7, 8, 9. A tie? 1, 2, 3. Neither. Good thing we're, oh, probably not in screen, so. All right, here we go. Get it hopefully near the center of mass so that it doesn't flip over backwards.
I didn't see anything. So
Tie.
It was a time.
It was a tie. Thank you. So physics by democracy does not work here. So the question is, why? Why does how fast it's going off the table, why does it not matter?
Because they were in different positions.
They're different positions.
Or it wasn't like the green one closer to the end of the table.
Yeah, that's why it wasn't going as fast, but if I pivoted in the right spot, they would have gone off the table at the same time. Riley?
Because gravity is the only vertical force on both of them.
Once it leaves the table, the only thing acting on it is downwards. And the acceleration due to gravity is relatively constant. It doesn't matter what the mass is of the object. Because they fall at the same rate, I can solve that problem by a useless information, X kilogram mass is slung horizontally off a cliff, make it a 50-meter tall cliff at an initial speed of 30 meters per second. How far from the base of the cliff will the mass land? Oh, I do need one other piece of information. 50-meter tall cliff near the surface of the earth. Let me draw the problem first. It gets slung horizontally. I know this is 50 meters. This is initially going at 30 meters per second. And I am trying to find what I'll label as R. It is a two-dimensional problem. First, questions on the problem itself. So the first thing, let's establish our convention. I hat, J hat. What's the positive I hat direction?
The right of R.
Okay. So put I hat this way. And J hat? Up. Okay.
Wait. Yeah, up.
Yeah. Okay. Up, or it's perpendicular to I hat, and it's a two-dimensional problem, so let's not do in and out of the board. But, you know, pick one, live with it. J hat. We're gonna solve two problems here. Because we have acceleration vertically, so we have a constant acceleration vertically, we have a constant zero acceleration horizontally. So we're gonna set up two problems. I'll have my I hat equation, I'll have my J hat equations. And so I have a displacement, initial velocity, final velocity, acceleration, and time. Time is the one thing that is going to be the same for both. It will be in the air vertically as long as it's in the air horizontally. I've tried to think, are there some bizarre physics exceptions to that? And I cannot think of a single exception to that. It will be in the air horizontally and vertically at the same amount of time. When you get to quantum physics, there's just some bizarre stuff that can happen. All right, so what do we know?
We know where's the right.
Acceleration,
Okay, horizontal or vertical?
horizontal, both,
Okay, horizontal, it's,
0,
and vertically,
9.
I will say there was a mistake there.
Is it?
Oh, it's negative 9.2,
Why is it negative?
because we are stopped,
Because what?
because downward is negative,
Why is downward negative?
because I said so.
Sure. Negative. If you had a positive there, given our convention that up is positive, you're throwing this off the cliff and it's going like that, up into the air. My experience in throwing things is it doesn't do that. Maybe I just lived a sheltered life. All right, what else do we know?
Our initial speed is 30 meters per second
Where do I put that?
horizontally.
Okay. We know two other pieces of information.
Displacement horizontally would be 15 meters. No. The vertically would be 15 meters.
Okay, vertically, displacement is what?
15 meters.
leaving out the minus signs is probably the biggest mistake I see here. So negative 50 meters vertically. Horizontally, we don't know, that's what we're trying to find.
Wait, I thought, isn't 50 meters positive? That we said j hat up is positive and 50 meters is up?
Where does it end relative to where it started? It ends down here. It started up there, so the displacement is down. We know one other piece of information?
The initial velocity is 0 for the vertical.
All right. We're trying to figure out how far it goes horizontally. We know two pieces of information. We could find the final velocity, the final horizontal component of the velocity. That doesn't really help us a whole lot. That is a time when we know three things, but we can't solve for the other two. What is the final horizontal velocity? So,
Zero.
not zero. No. Let's think about what we said here. We said the initial velocity is 30 meters per second, and the acceleration is 0 meters per second squared.
Oh, 30 is still constant.
Yeah, that's 30. The vertical is what basically determines the time. We're going to use this to figure out what the time is. And once we know the time, it's the same for both. And now that I know the time, I can figure out how far out from the cliff it goes. Just to give you a sneak preview of what we'll face tomorrow is, hopefully we'll finish that problem. Figure out what the final velocity is, but then make it more interesting and not have it being shot horizontally, but up at an angle or down at an angle. And then, given time, we'll potentially tackle the hardest of the projectile motion problems, which not everyone is as enamored of as I am, but this class will be different. You'll love the really hard problems. And I think we're done at 12:15 or 12:20.
It was 12:20.
12:20. Oh, we got another couple minutes here. Sorry to get you. I know you were all sad that it was time to go, but you got a little bit extra time here. What equation would we use in order to solve for time? Or a combination of equations?
Do we use the final equation like we did last time?
The VF plus VI over 2 times time?
Yeah.
Displacement? We don't know VF.
We would use the VIT plus half AC squared.
So if you want to find time in one shot, you would use that equation, the delta S is equal to VIT plus 1/2 AT squared. So in one shot, we can find time. If you want to do the intermediate step, because you hate doing quadratics because of some childhood scar, you can find final velocity first. The way that you would do it, you would find the final speed. Now you're going to end up with a positive number here. Well, first off, the F squared will be positive because if I throw something off a cliff, yes, it will fall. This problem makes sense that it can happen. If VF is, but we'll end up with a VF, which is square root of a positive number, we'll get by default a positive number. But the final velocity vertically is negative because right before it hits the ground, it's going downwards. And speaking of which, the problem was how far out from the bottom of the cliff does the ball go? The ball does hit the bottom. It is physics speak that when we say how fast, if I said how fast is it going when it hits the ground, the answer is not 0. Even though we talk about it's actually touching the ground, the question is really asking how fast is it going just before making contact with the ground. Because once it touches the ground, the acceleration is no longer constant. And so the way the problems are worded, we talk about it hitting the ground, but we really care about just before it touches the ground. And on that note, now you can cry because class is over. Or not, you know, I don't want to tell you how you react to it. I've watched enough murder mysteries to know people's reaction to grief is very different.